Let's take a look at how partial derivatives can be used in economics. Hit pause and read this question to yourself. What we have here is a function that describes a company's productivity. It depends on L, the number of units of labor, and K, the number of units of capital. And what we're being asked to do here is first we're being asked to find the marginal productivity of labor. In economics, a marginal anything is a derivative of that thing. And since they're asking for a marginal productivity of labor, they're asking us to take the partial derivative of this function with respect to L. Here's the function they gave us. Since we're taking the derivative with respect to L, it would make sense to rewrite the product of these factors in this way. It's not mandatory that you rewrite it this way, but if we do, we can think of this as a constant times a function of L. After all, if we're taking a partial derivative with respect to L, K is considered to be held constant. Therefore, the entire thing in the green parentheses is a constant. And that makes taking the derivative easy because the derivative would therefore be that constant times the derivative of L to the fourth. No product rule needed here. The derivative of L to the 1/4, as we know, can be found by the simple power rule, and that gives us the partial derivative with respect to L. Here I did a little algebra cleanup. You may want to hit pause and analyze that. Now, the question asks us to find this partial derivative, or this marginal productivity of labor, for specific L and K values. So now we can plug those values of L and K in. I did the work here without a calculator and then calculated it as a decimal. And therefore we have a marginal productivity of labor of about 15.6. What does that mean? I recommend hitting pause and reading that sentence a couple times. Remember, a derivative is a rate of increase or decrease with respect to some other quantity. And so if we're taking a derivative with respect to L, then the answer we get indicates how much the productivity function will increase for every unit increase in labor. Let's take a look at the second thing we were asked here, which was the marginal productivity of capital. That would be the partial derivative with respect to K of this given productivity function. This time, it might be better to think of the function this way, with the thing in the green parentheses being held constant. After all, if we're taking a partial derivative with respect to K, we're treating L as if it's not changing. And if the green parentheses are a constant, then the derivative can be taken easily without the product rule. Recall from basic calculus that the derivative can be used with the power rule. And then we can do a little algebraic cleanup. Okay, so we now have the partial derivative with respect to K in general. We're asked to find that partial derivative for specific values of L and K. Plugging those in and simplifying gives us 150. That's the answer to the question numerically, but what does it mean? You may want to hit pause and read this. Remember, a derivative is a rate of change of one quantity with respect to another. So the partial derivative of f with respect to k being 150 means every time k goes up by 1, f is going up by 150. And that's essentially what the sentence at the bottom of the screen is indicating. Here's our final example for partial derivatives in economics. Hit pause and read it to yourself. Here we're being asked to find the marginal profit with respect to 2x. Marginal always refers to a rate of change or derivative in economics, and so the marginal profit here with respect to x is the partial derivative of the profit function with respect to x. Remember that profit is revenue minus cost, and there's no revenue function given here. But there doesn't really need to be, because the revenue can be found to be 290x plus 440y. This is basic middle school, high school mathematics. If we're selling x of a certain item and they cost $290 each, then we will be taking in an income or revenue of 290 times x, or times the number sold. The same is true for 440y. So that revenue function is easy to generate on our own, even if we're not given it. The cost function they gave us, and so we plug that in. Here I've done a little bit of algebraic cleanup, no big deal. Now, we're being asked for the marginal profit, or the rate at which the profit is increasing with respect to x. So I'll take the partial derivative of this equation with respect to x. The derivative of 290x, if x is our variable, is 290, of course. The derivative of 440y with respect to x is 0, because if we're taking a partial derivative with respect to x, we're assuming that y is a constant. Obviously, the derivative of negative 35,000 is also 0. The derivative of this term with respect to x is clearly this. But if we're differentiating with respect to x, this term, which is being assumed to be constant because it has only y in it, would have a derivative of 0. And the last term, thinking of y as a constant, would give us a derivative of negative 0.47y. Now that we have the partial derivative with respect to x, or the marginal profit, we're being asked to find that numerically at a level where 100 of each item were sold. So if I plug in 100 for x and 100 for y, do some calculation, I get an answer of 231. And that's the answer to this problem. But let's take a moment to pause and think, what does that actually mean? Follow me on this logic. Marginal profit is the derivative of the profit. A derivative is a rate of change. So this partial derivative that we found is the rate at which the profit is changing with respect to x, which means how fast is the profit growing or shrinking? In this case, it's growing because the answer is positive. How fast is the profit growing for every single unit increase in x? Or to put more plainly, for every item A sold, after all, x is the number of item A that were sold, for every additional item A produced and sold, how fast is the profit changing, or how much is the profit going up by? If you're able to follow all that logic, read this sentence to yourself and it should make sense. And that completes our final example.